Last section we're going to look at as a review is hypothesis tests. We spent so much time focusing on that, and for good reason. It's a huge part of this unit that I'm not going to go super in depth with everything, but I'm going to cover the big ideas quickly here. It says, going through this list, explain the structure and goal of a hypothesis test. That is, we take someone else's claim. So someone says something, and we start with that. We assume that it's true, even though we don't believe it's true. We say, let's assume you're right. Then we go out, collect our data, and say, how likely is our data to occur? There's only a 7% chance of finding our data, or a 2% chance of finding our data if we assume that you're right. Then we use that value to decide if the claim must be true and reject it or not. If there's only a 2% chance of finding our data when we assume you're right, that's too unlikely. Therefore, you must be wrong. That's essentially how this process works. If we say, oh, there was a 12% chance of finding data as extreme as we did when we assume you're right, well, I suppose that's possible. I might be suspicious, but I don't have enough evidence to say there's no chance that that could happen. So that's the logic of the hypothesis test. You assume they are right. See how likely your results are under that assumption, and then reject from there. Second thing, it says, given the possibility of type 1 and type 2 errors when make a decision, think through which error might be worse. When you reject, you are statistically significant, you are number one. You may have made a type 1 error when you reject something. If you fail to reject, so type 1 happens when you reject. When you fail to reject, you may have made a type 2 error. Maybe you should have rejected, but you didn't. So failing to reject would be potentially opening you up to a type 2 error. Rejecting potentially opens you up to a type 1 error. If you're testing for a disease, this is the example here, if the null hypothesis is that you have the disease, what is worse? Is it worse to reject that you have the disease and say, oh no, you don't have the disease, and be wrong? So if you tell someone they don't have a disease but you're wrong as the physician, that'd be really bad. Type 2 error in this situation would be you let them continue to believe that they have the disease because you don't reject that they have it. So you say, yeah, I think you have it, and it turns out that they don't. In that situation, they're going to get probably nervous and worked up. They might get some extra medical testing, but eventually they're going to be cleared and realize that they're okay. So the first person is told, oh, have a great day, and then they're going to keel over on the street one day. That's really bad. The other person might be told that they have something they don't, go incur some additional stress and expense, but probably be okay in the end. So in this case, a type 1 error would be worse. You could rearrange the hypothesis such that the null is that you don't have it. In that case, a type 2 error would be worse. So it's all dependent on how it's set up. Next one, it says 0.05 is a typical alpha value. Why? And then what should you think when you get a p-value that's a little bit off of that, let's say 0.06? 5% is a nice, clean, round number. I have 5 fingers on my hand. 5% rolls off the tongue. It's a reasonable value. It's more than 2 standard deviations each direction. Is kind of another thing that makes it a nice round number. There's nothing special about 0.05 other than 5% seems unlikely enough for most people. 10%, like, oh, that could still happen. 5%, now I'm really suspicious. It's an arbitrary number. So a p-value of 0.06 is almost as good. You should be really suspicious about being right when you get something that's 0.06. If you get 0.04, you shouldn't be like, oh, I've proven everything beyond all doubt. No, it's kind of a sliding scale. We have to have the cutoff somewhere. Why is 60% passing for a class? I don't know, because someone picked an arbitrary number and we said 60% is good enough. We could have made it 63%. The point is that 0.05 is a pretty good arbitrary number compared to other options we could have picked. So just know that there's nothing particularly special about it. Continuing on, why is a two-tailed test generally a bad approach unless you truly have no reason to guess either direction? When you do a two-tailed test, if you look at your normal curve, you need to have a z-score of about 2 to get under 5% because you're shading in both tails. If you want to get under 5% with one tail, you can get away with maybe 1.7, 1.8 as your z-score. The point is you don't actually need to find that big of a difference to get 5% in one tail. To get 5% collectively to show up over two tails, you need to find a much bigger difference. So it's actually harder to prove something if you're basically doubling your p-value. If you copy that one p-value into both tails, it's really hard to prove your point. So that's why, if possible, pick a direction. If you're designing a new drug and you're supposed to make people get sick less often, only look on the lower end. Don't look on both ends because you're making it harder for yourself to prove something. So that's why we have one-sided hypothesis tests. Is it's easier to prove your point if you only look on one side. Continuing on, a hypothesis test proves a statistically significant difference exists between the null and the sample data. Sometimes it proves a difference that has no practical importance. Why? What do I mean when I say that is what I should say. What do I mean? Let me think about my own sentence here. A hypothesis test proves a statistically significant difference, but not a practical difference. I might have a p-value of 0.04. That means I proved statistically whatever I was setting out to prove. But let's say I proved that the average height of people is less than 5'8", and it turned out to be 5'7.5". Does anyone really care? Probably not. So being statistically significant might make you right, but if nobody cares about your results, then it's not that practical. So just be aware that proving something statistically doesn't mean that it is necessarily useful to society. That's all we're getting at with that. Continuing on, working through this entire process, if you're given a scenario, and we'll go look at the scenarios at the bottom, you need to go through the process of deciding what is being claimed. What is the null hypothesis? What is the researcher's thought about this claim? That's going to lead to your alternative. If you were to go out and challenge it, what questions would you ask? And we'll talk about that. But basically, think about how would you collect the survey data. Is that going to be quantitative, or is it going to be categorical data? How are you going to summarize that? Categorical gets summarized as a proportion, quantitative as a mean. And that'll help you decide how to write that null and how to write the alternative. Knowing how to write it with the symbols, mu or p, is really important. We're not going to focus too much on the subscripts. That's just a way of describing p and mu a little bit better. What is a reasonable cutoff? AKA pick 0.05 all the time unless you have a reason to say I need a stricter or less strict alpha value. Are you going to perform a test of the mean or a proportion? Well, it depends what kind of data you're working with, and the direction left, right, or two-tail will depend on your alternative hypothesis. Assumptions you need to check. You always need to check for random data, for like an SRS, and then the other assumptions depend on what you're doing. If you're using a normal curve, you might need to check for certain things for both means and proportions. Need to know how to use stat key to do your hypothesis test. Need to know how to use the z-score and then the normal curve to calculate a p-value as well. We want to know what the p-value means. It tells you the probability of finding data as high, low, or extreme as you found when you assume that the null is true. And we'll go through specifics later. Describe whether or not to reject the null. That's based on your p-value less than 0.05 or less than whatever you pick as your alpha cutoff. Then you would reject. Otherwise you would fail to reject. When you reject, your data is statistically significant, and you should be able to describe what you actually did. You would say, we assumed this to be true, find our data was really unlikely to find in that situation, therefore we rejected the initial claim. So being able to interpret a sentence not necessarily write it in the case of a multiple choice test, but read it and understand it is important. And then finally, imagine what you found later on. You actually found the true answer. Could you determine if you made a type 1 or type 2 error? When you reject, you could have made type 1. When you failed to reject, you could have made type 2. So let's go through these scenarios quickly. A factory manager claimed that production of Nerf darts resulted in darts that were an average of 2.3 inches long. Smells like claim, smells like null hypothesis. So that's probably our null. Before making a large order, you suspected that it might be wrong. So you have an inkling as the researcher. You randomly selected 40 darts off the end of the line during the next day to collect your own sample and check the manager. You found the sample average of 2.24 inches, standard deviation of 0.13. To be careful not to falsely accuse the manager of being untruthful or having a defective factory, you chose a different alpha value, 0.01. So this would be an example where you don't use 0.05, but you use a different thing, 0.01. Going back, let's check our direction. The very first thing says, what is the claim? 2.3 inches. What is the researcher's thought? That it's wrong. Doesn't say higher or lower, it just says wrong. So we're thinking two-tail, not equal test. It says you randomly selected, so we're thinking sample now. Randomly selected 40 darts. You found a sample average of 2.24, sample standard deviation of 0.13. I'm going to go ahead and label all of these things real quick. Sample standard deviation is going to be SX. Sample average is going to be X bar. A 40 darts is going to be our N, our sample size. This is going to be our average, our claim, that mu is equal to that. And here we're going to say that mu is not equal to that 2.3. So working through these things, we talked about the first two. Go out and challenge it. What question would you ask or what would you observe? We're talking about Nerf darts. So every Nerf dart I would take off the line, I would say, how long are you? I would measure it. So I'm looking at a length, a distance, a number. So I know that I'm dealing with quantitative data. The null hypothesis is that mu equals 2.3. So the null is that mu equals 2.3 inches. The alternative, then, is that mu is not equal, because we didn't have a particular direction in mind. So not equal to 2.3. Our cutoff, our alpha value is 0.01, because we are told to use 0.01 instead of 0.05, so we need to do that. What test are we going to perform? We're going to perform a test of the mean. We're going to perform a two-tailed test, because it is a not equal test. Assumptions we need to check. We need to check that we have randomly collected data. Let's take a look. It says you randomly selected 40 darts off the end of the line during the next day. So it seems random enough for me. I'll go with that. And that's all we need for stat key. For test of the mean, other assumptions we would need to check would include, and we get this straight off of our reference sheet, we need to check that we have a random sample. We did that. A population that is greater than 10 times the sample size, and a sample size of at least 30. It says we selected 40 darts, so we're okay with the sample size of 30 thing. If we're thinking about a Nerf dart factory, I'm guessing there is more than 40 times 10 or 400 Nerf darts at the Nerf dart factory. So we're probably doing okay with our population size being big enough. So all of those assumptions appear to be met. Continuing on, find the p-value using stat key. If we pull up stat key here, we are going to be looking at a test of the mean. So a hypothesis test for a single mean. If I gave you a list of numbers, we would edit the data and we would type in the list of numbers that we were given. Now, for this particular problem, because we're just kind of using it as a general example, I don't tell you all the numbers. So you actually cannot do the calculations in StatKey for a mean. For a proportion you could, because all you need is your successes out of your total. For the mean, you need the raw data, all the numbers, which we don't have, so you actually cannot do this calculation. So we're going to skip StatKey. Next one says find the z-score using the normal curve operations. Back to our reference sheet. We look for how we get our z-score down here for quantitative or means. It says z equals our sample average minus mu, the population estimate, or the null hypothesis here, mu, divided by that sampling standard error, the s over square root of n. Our x bar that we collected is 2.24. Our population null hypothesis here, 2.30. And we're going to put that all over our standard deviation, 0.13, over the square root of our sample size, square root of 40. So on top, if I subtract these two, I get negative 0.06. So I am 0.06 below average, or below the null. On my bottom, I have 0.13 divided by the square root of 40. You get 0.02, 0.055. I take negative 0.06 divided by my last calculated answer, and I get negative 2.92 approximately as my z-score. So that would be my z-score. From there, if I want to get a p-value out of that, I need to plop that on the normal curve. It's going to be way down here, and it's going to be shading to the left of that. I'm going to be doing normal CDF of negative infinity, or negative something large, to negative 2.92. And when I do that, I get a p-value of 0.0018. If I round it up, 0.0018. That is my p-value. Now, continuing on, once I have that p-value, it says describe it in a sentence. There is a, if I were to turn this into a decimal, or a percentage, there is a 0.18% chance that I would find a sample average as low as, or as extreme as, because it's not equal, sample average as extreme as 2.24 when we assume that the population mean equals 2.3 inches. So there's a 0.18% chance of finding a sample average as extreme as as extreme as 2.24 when we assume that our population average is 2.3. Our next step then is to decide whether or not we reject. Is 0.0018 less than 0.01? Yes, it is. So we do reject. And that makes our data statistically significant. So reject, significant. State our decision in context in a short sentence. We would say that we reject the claim that mu is equal to 2.3 inches in favor of the alternative that it is not 2.3 inches. And then finally, later on, if we rejected and we found out that we had made the wrong decision, we would have made a type 1 error. I'm not going to actually go through the calculations for the next one, but I am going to talk through the concept just to make sure you've got the big picture of that. So this second one is dealing with proportions, but let's go ahead and make sure we know why we could figure that out other than saying it's not the one about means. It says, at Twitter Math Camp, which is a real thing, and I did go there. Yes, I'm a nerd. A speaker said that 8% of U.S. math teachers had a Twitter account. You think that estimate is too high, and you collect an SRS of 120 U.S. math teachers. 6 said they had an account. The question that's being asked to the math teachers in the sample is, do you have a Twitter account? And the claim that's being made is that 8% of the population has one. So our null hypothesis is going to be that P is equal to 8%, or 0.08. You think the estimate is too high. You think it is lower. So you think the actual answer is lower. So you would say that P is less than 0.08 is your alternative hypothesis, and that's what you're seeking to prove. You ask each teacher that you sample, do you have a Twitter account? It's a yes-no question, meaning it's a proportion that you're dealing with. When you collect all your data, 6 out of 120, that is your p-hat, and that's what you'll use in your formulas or you'll plug into StatKey. One of the issues that will come up is when you check your assumptions, you don't have at least 10 successes and 10 failures. You have plenty of failures. You don't have 10 successes. You only have 6. So that might cause problems with your assumption that you have a normal curve for your sampling distribution. Eventually you get down through all your data, you'll have to decide whether to reject or not, and that's going to look the same as it does for the means. Once you get to the bottom part, it's all going to be the same process. So that one you'll need to do on your own. But hopefully this review gave you a good start, was able to kind of check some of the big ideas, and if you're following all of this, I think you'll be in excellent shape for your assessment. Good luck.